certain other characteristics of operational amplifier. Let us see in this video. The very important one in the op-amp characteristics is the so-called CMRR. CMRR stands for common mode rejection ratio. Generally, it can be defined as the ratio of the differential voltage gain AD to the common mode voltage gain ACM. That is CMRR equal to AD by ACM. The CMRR indicates the ability of the operational amplifier to reject common signals appearing at the two input terminals. So what is the main advantage of this high CMRR? Normally the noise signals or unwanted signals, they appear as identical signals at the two inputs of the operational amplifier or differential amplifiers. So this high CMRR is able to cancel or reject those noise signals, identical noise signals appearing at the two input terminals of the operational amplifier. The common mode voltage gain can be determined from the equation ACM equal to VOCM divided by VCM, where VOCM is the output common mode voltage, VCM is the input common mode voltage, and ACM is the common mode voltage gain. Generally, CMRR is very large. Being a large value, CMRR is most often expressed in decibels. The next parameter is slew rate, SR. The slew rate, SR of an operational amplifier is the maximum rate at which the output voltage can change. When the SR is too slow for the input, distortion results. So you can see we have a voltage follower and VA is the input signal. So this is illustrated in the above figure, which shows a sine wave input to a voltage follower producing a triangular wave output waveform. The triangular wave results because the op-amp output simply cannot move fast enough to follow the sine wave input. The equation relating SR slew rate, output voltage change and time is SR equal to delta V naught divided by T. Next we shall see briefly frequency response of operational amplifier. The gain of an ideal operational amplifier is infinite. However, the practical operational amplifier gain decreases, that is, rolls off at higher frequencies. So as frequency increases, the gain gets reduced in the case of a practical operational amplifier. So the reason for this is a capacitive component in the equivalent circuit is responsible for this. This capacitance is due to the physical characteristics of the device, the internal construction of op-amp. the magnitude and phase angle of the open loop voltage gain are a function of frequency and can be written as magnitude equal to AOL. AOL is open loop gain divided by square root of 1 plus F by F1 the whole square, and the phase angle phi equal to minus tan inverse of F by F1. The magnitude and the phase characteristics are shown in figure. F is the frequency and A is the gain in decibel. It can be seen that for frequency F lesser than F1, the magnitude of the gain is 20 log AOL in decibels. At frequency F equal to F1, which is the cutoff frequency, the gain is 3 decibel down from the DC value of AOL in decibel. This frequency F1 is called corner frequency. Sometimes it's also called cutoff frequency. For F greater than F1, the corner frequency, the gain rolls off at the rate of minus 20 decibels per decade. So this diagram is the approximation of loop gain versus frequency. So it's called approximation of loop gain, open loop gain versus frequency curve. So x-axis we have taken the frequency and the y-axis represents the open loop gain. Up to F1 the gain is almost constant, and after that the gain rolls off or reduces minus, that is 20 decibels per decade. 20 decibels per decade up to some frequency F2, and then from F2 to F3 it reduces at the rate of 40 decibels per decade. After that, after the frequency F3, it rolls off or it reduces 60 decibels per decade.